I hope all of you are well today. I am Mr. Ish. Thank you for joining me. This video is an interesting one. It is the result of a inquiry from a particular viewer, a confusion they had with regards to toroid-like object volumes. Generally, students use the word toroid and torus interchangeably, but there's a clear difference between the two different terms. However, in this video, we're just referring to everything in a generalized manner, a toroid-like object. These are objects which have the potential to develop a donut-like or a ring-like structure, a solid. What is the confusion I'm referring to? It's the confusion which the student had with regards to this here and this representation, where the circle area is equal in both representations. Here the line of rotation is y-axis, here again it's y-axis. But you can see clearly what the difference here is. In this particular case, you have a major radius and you have a minor radius. Here you have a major radius obviously and you have a minor radius, but you can visually see what the difference is. In this particular case, the major radius is equal to your minor radius. Here your major radius is larger than the minor radius. When you do a three-dimensional solid for this representation, you know what your solid will look like. It will have the potential of a donut shaped solid, but it's not going to be having the space in the middle. But if I were to generate the solid, it would look something like this, and my drawing is not very good, but this would be right here, the three-dimensional structure that you would see. A potential for a toroid-like object to develop with a space in between, but there is no space over here. In this particular case, you have a solid which generates like this. In this case, you have a donut-like structure which develops because you have a space develop in between. That space, as you can see, would be right over here. There's a certain space over here. As you can see here, there's no space. There is a confusion with regards to these two. Are the volumes of these two representations represented by the same formula, or the volumes generally represented in an equivalent manner? And I'm going to eliminate that confusion in this video. How can we go about doing that? Well, what's the equation of what you see right here? A circle with a center at the x-axis. You can say x minus h whole square plus y square equals r square. The center here is h comma 0, and you know it. That's what it is. What's the equation of this circle right here? Again, it would be x minus h whole square plus y square equals r square. You are still on the x-axis and your circle center is still h comma 0 right here. In this particular case, or in both of these cases, the center of the circle also gives an indication of the distance of that circle from the origin, because your circle is having a center on either the x or the y-axis. The value here can give you an indication of a distance, as it will do so in this particular case too. It's an instance of a distance. You're h units away from the origin. Supposedly this circle has a center 1 comma 0 and this has a center here 5 comma 0. In this particular case, you're 1 unit away from the origin. Here you're 5 units away from the origin. The center in both cases is giving you an indication of distance. Keep that in mind. In this particular case, the distance h is also synonymous with your major radius. Here again, the h is synonymous with your major radius. In all instances of a circle, the centroid, you know the centroid having the x bar and the y bar value, in all instances the circle center is the centroid. If this right here is the center of my circle, the centroid is also h comma 0. And if h is equal to r, then my centroid can be written as r and then 0. In this particular case, the center is also the centroid, and here h is equal to r. Therefore, the centroid here is also r comma 0. What's the difference between these two in terms of dimensions? Nothing other than the value here or the value here. Or you can say the h value and the h value. That would be the only item here which would create the difference, because earlier I already told you these circles have same area. The radius, the minor radius must be equal. The difference lies over here, or in terms of the h values. If I were to use, let's say, the theorem of Pappus, volume is equal to area times the distance, which you know can be area times 2 pi x bar value, or it can be area times 2 pi y bar value of your centroid. The area of this representation is a circle, pi r square. What's the distance? The centroid, or the center going through one rotation. Here I'm looking across the x direction, so I have to obviously use x bar value. What's my x bar value here? It's an r. Combine all of this. It's a 2 pi square r square r. But if I'm telling you here already at the beginning r, the major radius is equal to minor radius, you can also say this as 2 pi square r cube, because this r is equal to your minor radius. It can be equivalent to that expression as well. In this particular case, what's the volume? Well, again, it's area times distance using the theorem of Pappus. Pi r square again is the area of the circle, region of space. In both instances, the region of space is located only on one side of your line of rotation, not shared or overlapping across both sides. What's the distance is going to go? 2 pi times again the x bar value. I'm looking at the x bar value, which is here r. Here I'm going to get 2 pi square r. In both instances, I'm getting an equivalent volume formula. So that tells you when you have a structure over here which is going to develop with no space, you will have still a toroid-like object develop, which would have an equal representation in terms of a volume formula as would a true toroidal-like object, where you do have a space developed within that ring-like, donut-like structure. Again, the representations are the same. The only difference between these two representations would be the actual numerical value of that volume. The formula are still the same, the volume formula is still the same, but the volume numerical output be different, because between these two cases you'll have a different r value. The volume of this solid will be much larger because this major radius is a larger value. The volume of this solid, eventual solid, would be smaller because the major radius is a smaller value. Simple as that. But the confusion with regards to this solid and this solid, the solid I showed you at the very beginning, are they the same in terms of volume formula? Yes, they are. So don't be confused with regards to that. All toroid-like objects can be represented in terms of volume by this type of a formula: 2 pi square r. Major radius, minor radius, your pi, and 2. Keep that in mind. Thank you for watching.